All right. Good afternoon. I'm a research geophysicist with the USGS in Santa Cruz with Danny Brothers. This afternoon, I'm going to present some preliminary observations and some recently collected data from Lake Chelan, the third deepest lake in contiguous United States. So if those of you that are familiar with Lake Chelan, it's really long, it's really skinny, and it's really deep. On the southern end here, we have Chelan, the city of Chelan. Moving a little further north, you've got the city of Manson, and all the way up at the northern end, which is in the national park, is the Stehekin and the Stehekin Delta with the Stehekin River, which we'll talk about today. Next. All right, in addition to the records of ground motion that may be present in the lake, there might also be high precision records of Cascadia volcanism, as well as evidence of glacier retreat and advancement. In June of 2023, we deployed the USGS research vessel, the Parks Navely, from which we collected high-resolution multibeam bathymetry, seen here in this map, as well as seismic reflection profiles and sediment cores throughout Lake Chelan. These new data pair really well with the new LiDAR recently released from Washington State's Department of Natural Resources here. Everybody can access these new LiDAR data from the LiDAR portal. Next. As has been put out before in the earlier talks, lacustrine environments and the sediments within are faithful record keepers of continuous post-glacial sediment records, within which we find punctuated deposits triggered by regional earthquakes, volcanic eruptions, and floods that we are obviously going to pursue in pursuant of the USGS's various mission areas, more importantly to identify risk assessments and methods and their usage and improve the understanding of earthquakes occurrence and their effects and consequences. Next. So like Dan said, or Jeff said before, we've moved a little bit to the east. So on this map, we've got the state of Washington. In the red box here, we've got our Lake Chelan survey area. Blues are obviously all of our national parks areas that we were talking about during this during the talks throughout this symposium. And then within Lake Chelan, we see that this is pretty close to the center of the 1872 earthquake in central Washington. It's a large magnitude earthquake. It was felt from British Columbia to Oregon and from the Cascadia coast to Montana. Much of what we know about this earthquake was gained through personal accounts and sparse newspaper articles from the time. Next. Recently published research from our USGS colleague Brian Scherer documents deformation along the Spencer Canyon Fault just south of Lake Chelan in that map. So here we can see this sliding feature right here in this LiDAR. Next. Where terrestrial paleoseismology methods were able to date recent offset along this fault to this large 1872 event. So we had our colleagues used trenching methods to date this offset using C14, as well as I think maybe some tree dendrochronology on this survey, maybe not. So we're seeing deformation from this 1872 event. Next. While we've typically relied on terrestrial paleoseismology methods to identify and document regional earthquake histories, this methodology has a skewed earthquake catalog, as only large magnitude earthquakes of magnitude 7 and higher are usually required to produce surface deformation. Next. On the other hand, lacustrine environments have a much larger bandwidth for recording earthquakes, as they are capable of recording earthquakes of a much lower magnitude, magnitudes of 5 and greater. Next. This is because, as we've kind of discussed earlier in these earlier talks, lacustrine paleoseismic methods do not rely on primary evidence, such as fault offset within lacustrine environments, whereas we have secondary evidence or proxy evidence from ground motion. So essentially what we have is earthquakes are going to shake the ground, destabilize shelf and slope sediments, where these sediments are going to be transported down slope. Next. All right, so in this next slide, we're going to be kind of talking about the three major types or three main ways that sediments are going to be deposited within these lacustrine environments. We're going to start off on the bottom left here where we have settling. These are usually fine-grained sediments that are fall out of the water column and drape over the underlying morphology. These are the background sediments that we've kind of been talking about. And the analogy I like to use here is snow falling without wind. So we've all kind of went to sleep during a snow, we wake up and there's a nice layer of snow that's draping over bushes and our cars and trees and everything. These are our background sediments. Let's go to the upper example. We have current controlled sediments. These sediments are laterally transported with some sort of current and in which we usually create drift. These are our snow drifts are an example of this. And finally, gravity. These are our turbidity currents that are rapidly transported downslope, filling available space. These are our avalanches. So we've got snow falling without wind, snow drifts, and avalanches are our kind of analogies. And we're going to kind of look at those with some of our data on the next couple slides. So next. So here we have our background sediment. These sediments are going to be deposited flat, and we're going to have parallel reflectors. So the snow is kind of draping down, and we can see this is our background. So these are without any major events happening. Next. Here we have current controlled deposition, and this is going to be when we're controlled by some sort of flow. So here we have the cold, dense water coming from the Stehekin Delta here on the right in our multibeam data. That's going to be creating this hyperpycnal flow that's going to create these bed forms. So here we have an example of current controlled deposition that's very similar to what we see when snow wind blows and we have snow drifts. Next slide. And lastly, we have our gravity flows. These are going to be our proxies or what we are going to look for to infer that there was some sort of ground motion that induced these failures. So a couple things happening in this slide. So on the upper left, we have a multi-beam image that is kind of showing where we have a kind of a hummocky or kind of blocky deposit. We have this kind of black line right here that's actually the fault scarps and slides. So these features are pre-analogous with each other. In our bottom section right here, we have a seismic profile showing this kind of chaotic upper section of this gravity flow. And we can also see some of the background. So we can see that we can kind of pull these two different deposits away from each other when we see our fine laminated deposits. These are our backgrounds, and these are usually interrupted by these high, these are our density deposits. All right, next slide. So here we're going to highlight some of our coring capabilities. So here we've got our two cores from the two cores in the previous section where we have our high resolution photo scans on our lefts, and then we have our X-ray CT images on the right. So these data allow us to really understand what the different density structures are within our cores and allow us to kind of understand a little bit better where deposits are and where the base of these deposits are, as well as identify tephras as well as other important stratigraphic markers within our cores. So next slide. So here we can see that the bottom of this deposit right here, highlighted in brown, has a coarse, kind of more dense base that kind of goes up to this more mucky layer. And then it kind of fines up to the kind of gray buff area where it fines out and has this nice little clay cap at the top. And this is kind of the textbook signature of what one of these deposits that could be an earthquake resemble in the different profiles that we're looking for. All right. We also have this, oh, can you go back one, please? We also have a volcanic tephra that's highlighted in this green right here. We're not exactly sure what that is. We haven't sent that out to be tested, but it could be likely Glacier Peak because it's so close. All right, next slide. All right, and then we can kind of understand what all the different reflectors are we're looking at when we use the cores. Next slide. All right, next. All right, so then that's the next 2 minutes of the talk. We're going to kind of go fast here. We're going to work our way from the south to the north, kind of highlighting some of the cool features that we see in the lake. So we have in the southern part of the lake, it's kind of characteristic of these kettle structure where we have these little depressions. We also see that the southern part of the lake is kind of dominated by a bunch of these failures. So these kettles, next slide, these kettle structures are these little depressions, and we can kind of image these through using the seismic data. And next slide, what we think is happening are there was ice that was kind of entrained in the till. The ice is gradually melting, and as the ice melts, it creates available space where the sediments then are going to infill these holes. So the southern basin of Lake Chelan is dominated by these features. Next. Next. All right, so as we move forward, we're starting to see more glacial features, but we're going to kind of start losing our kettle morphology next. And we start to see that the bathymetry of the Lake Chelan is kind of dominated by a bunch of these submarine fans. So all of the sediment that is coming into the lake from these steep water catchments on both sides are kind of building out these features that we didn't know really existed before we did this high resolution bathymetry. So you can kind of just cycle through the next rest of the slides on our way up. Okay, let's keep going. All right, stop right there. We have our deepest part of Lake Chelan. I'm sure someone is going to have a question about that. You can keep going a little further, keep going all the way to the top. So these are great data. We're just scratching the surface of what we can do with them. Obviously, our primary objectives are to understand the earthquake hazard potential from this area and how it's recorded in Lake Chelan. But if anybody has any ideas of how we can use these data to answer any other questions, please let us know. And with that, I'd like to advance the next slide and thank everyone that helped us get this work done. Lots of people in the National Park, DOE, Lake Chelan Research Institute. And with that, I'll hit the next slide and open it up for questions.
All right, thank you, Bo. Any questions for Bo here? I don't see any in the chat. So if you have any questions, you can raise your hand or you can put the question in the chat. Comment about the great analogy to snow. Yeah, I agree. That was a very good analogy. Here we go. Robert from Department DFW says, do any paleolimenologists examine, I should know that word,
SAICH
impacts of earthquakes? There we go.
Well, there are historical, I wouldn't say records, but there's anecdotal evidence of SAICHs from a lot of the historical earthquakes that have happened in the Pacific Northwest. Lake Chelan would be a great place to study SAICH because it's so long. So we have this great time sequence of the response. So the SAICH is essentially, you might have some event and it's basically just water sloshing around, right? So it might create some event or some marked response to the watershed on one side, and then it might happen on the other side too. So I think that's something we can look forward to. Not yet.